Hi there. Welcome back to another lesson in AP Calculus. We're coming to near the end of Unit 7. We got a couple more lessons left to go. Unit 7 has been all about integration. We've learned about the definite integral, the indefinite integral, and the connection between the two through the first fundamental theorem of calculus part that we've looked at. Today I want to talk more about the fundamental theorem of calculus. Particularly, we're going to talk about accumulation, and we're also going to look at some special cases. So let's get right to it. A function that has a y-axis symmetry is called an even function. And it gets that name because of a polynomial with y-axis symmetry has even exponents. But they can look in a variety of different ways. So an even function. A function that has origin symmetry, where you can rotate it around the origin, has odd symmetry. We call it an odd function. So if f is an even function, then it might look something like this. It might come like that and then come up here. But then whatever it does on the left, it's going to do on the right because it is symmetrical across there. So the area of this function would have to be, the area under the curve but between the x-axis. So all of this, right, that would be from negative a to 0. And then we'd have, like, all of this would be from 0 to a. So the area from negative a to a would have to be twice the integral from 0 to a because they're equal on each side. Now, if we had an odd function, an odd function, again, it can look like all sorts of different things, but it has to be symmetric about the origin, meaning that, if I did this correct, I could rotate it and it would look the same if I did a 180-degree spin. And so if this here is like negative a, then this area here, because it's all underneath the x-axis, is all going to be negative. And, if we go over here to positive a, this is going to be the same area, but now, this is negative because it's below the x-axis. This is positive because it's above the x-axis. So negative over here, positive over here, would absolutely cancel each other out, making 0 if you go from negative a to a. So let's just look at a couple of quick examples of these special cases that come up. So given that f of x is even, if the integral from 0 to 5 of f of x equals 3, then what would be the integral from negative 5 to 5? Well, it would be 6. What about from negative 5 to 0? Well, because it's even, we know they are the same area, so it would be the same value. This here is just a reminder that we can pull a constant out. Oops. So the integral from negative 5 to 5 was 3, and if you multiply it by 4, you get 12. Over here, though, the integral from negative 1 to 0 of 5x, well, let's try our u substitution. Let's let u equal 5x. So d equals x dx. Oh, I'm sorry, just 5 dx. I'll divide both sides by 5. I get 1/5 du equals dx. So this becomes the integral. I got to plug in negative 1 times 5 is negative 5. 0 times 5 is 0. I got a 1/5 out here. F of u du. Now the integral of f of x from 0 to 5 is 3. So the integral from negative 5 to 0 of f of u would be also 3 because it's an even function. All that's different is the letter, but I could call this x, u, z, q, whatever. So this is just 1/5 times 3, or 3/5. All right, I got a practice problem for you to do, so please pause the video and give it a try. All right, so the integral from negative 5 to 5. Keep in mind that the integral from negative 5 to 0 would be the opposite of 3, so negative 3. So combined, that makes 0. because this integral here is -3. And from -5 to 0 is -3, and 0 to 5 is +3. So from -5 to 5 is 0. And so for this is just 4 times 0. It's still 0. All right, let's take a look at this next one. We're given that dy dx is equal to 3x squared plus 4x minus 5 with the initial condition of y of 2 equals -1, and we're asked to find y of 3. Well, there's a couple different ways we could do this problem. We need to find y of 3. So let's find the equation for y and evaluate at 3. So this is kind of the way that we would do it based on what we've been doing so far in this unit. So y as a function of x is, if I raise the exponent by 1, I get 3x cubed over 3. That's just x cubed. Okay, and then 4x squared over 2 becomes 2x squared. And then minus 5x plus unknown constant c. But we were given an initial condition, so we can solve for it by plugging in 2 for x and -1 for y. Let's see, that becomes 8 plus 8 is 16, minus 10 is 6. So it looks like c is a -7. So we have y of x is equal to x cubed plus 2x squared minus 5x minus 7. And I'll just evaluate y of 3. Well, y of 3 would be 27 plus 18 minus 15 minus 7, which is 38 minus 15 is, I think, 23. All right, now that's one way of doing it, but it's actually kind of a little bit too much work. Let's do it a different way. Let's use the fundamental theorem of calculus. So we know that the integral from a to b of f prime of x dx equals f of b minus f of a. If I solve this for b, I can simply add f of a over in front of here to both sides, right? Adding it to both sides moves it over there. So what that means is, if we're trying to find f of 3, or in this case it's y of 3, well, y of 3 must be equal to y of 2 plus the integral from 2 to 3 of y prime, which was dy dx, so 3x squared plus 4x minus 5 dx. Again, so I know that the integral from 2 to 3 of this equation is equal to the antiderivative at 3 minus the antiderivative of 2. I just moved the 2 over. Y of 2 is -1. So then we have -1 plus, let's integrate again. This is x cubed plus 2x squared minus 5x. And we're evaluating this integral from 2 to 3. So then I get -1 is equal -1 plus 27 plus 18. 27 plus 18 would be 45. Minus 15 is 30. Then I got to subtract. Now I got to plug in the 2. I get 8 plus 8 is 16. Minus 10 is 6. Right? Let's see. 8 plus 8 is 16. Minus 10 is 6. So I end up with a -1 plus 30 is 29. Minus 6 is 23. Less work and gets us the answer that we need. So that's kind of a common problem. Now, this second method, rearranged, the second form of the fundamental theorem of calculus shows us a really neat equation that I call the accumulation function. I and quite a few other people, but you don't always hear that name. But this is what we're going to call it. We're going to call it the accumulation function. It says that if f is continuous on the closed interval from a to x, then I can always find f of x by simply starting at f of a and adding all the instantaneous changes from a to x. So I want you to think of it this way. F prime is all of the incremental tiny changes in f. f of a is where we start. So we have our starting y value. We start, and this is how much we change. And that tells you where we finish. You know, if I start on the 10-mile marker of a highway and go 60 miles per hour for an hour, I'm going to end up on 10 plus 60 equals 70-mile marker. That's all this is saying. It's just it's adding, it's accumulating all these little instantaneous changes and adding it to our starting amount. I also like to think of, the pumping water into a barrel kind of thing. The integral is telling you how much water was pumped in, but you have to add it to how much was already there to get the new total. The accumulation function says that if you want a new value of b, then start at f of a and add all the instantaneous rates of change of f from a to b. Now, the way they test this on the AP exam is they put it on the calculator section, and they give you things that are known not to have a symbolic integral. For example, e to the negative x squared does not have an integral. It's actually called the error function is what its integral is. So unlike a derivative, we can always take a derivative of a function. You can always integrate. And so they're giving you ones that if you type that into a calculator and try to find the integral with your TI-89, I got an emulator up here. Let's take a look at it. So I'm going to say, hey, I can solve this. I can integrate it and then get my C value using this, and then find f of 2. Easy, right? So I say integral of, sine, why is it saying that? Oh, I'm not reading that right. I'm pressing the wrong button. Sine, they're kind of blurry on this picture, isn't it? Sine of x squared dx, close parentheses, I get the integral of sine of x squared dx, because it's not know what to do. It says, well, whatever it is, that's it, right? Because it's still useful information, but it's not something the calculator or a human can do. So that's why they ask those questions, to make you know that accumulation function. And this is how we're going to write it out. Whatever you want to find. It doesn't, and here's the deal, it doesn't matter if it's after or before this one. This happens to be after. Doesn't matter. It goes either direction. You say, what do I want to find? That is equal to, what am I at right now? Plus the integral from what I'm at to where I'm going. This number here goes here. I don't care if this integral seems backwards or not. This one looks normal, but it can go either direction. Of f prime of x dx. So we're going to write that out. We're going to plug in. We're going to say -5 plus or minus the integral from 1 to 2 of sine of x squared dx. And that's what you would write on a free response question if you had to. And then we're just going to do it. So we'll say -5 plus the integral, second 7, of sine of x squared, comma x, comma 1, comma 2. Now, hit diamond enter to get the decimal approximation. Or you can actually set your mode to always be approximate. You check the pretty print, make sure it looks in like what you typed in, and that's the answer. -4.509. I think that was a 9 at the end that didn't round up. Oh, it's a 5, actually. There you go. But it doesn't round up. All right, let's try the next one. Again, e to the negative x squared, definitely something we can't evaluate. But that's okay. F of -1 is equal to f of 4 plus the integral from, what did I say? This goes on top. This is where you want to end up. Where you want to end up goes there. So yeah, it's backwards, but this number here goes there. Because this is adding a change from to 2. It's perfectly fine to be negative. All right. Of e to the negative x squared dx. 3 plus the integral from 4 to -1, e to the negative x squared dx. Yeah, I always write it with that f of 4 first so I can see that 4 at the bottom. I want to see that to make sure you do it right, because this is an easy question. We should expect to see it on the test, and we do not want to get it wrong. And it's easy to get wrong if you put your numbers in backwards. So 3 plus the integral of e to the x squared, negative x squared to be exact, comma x, comma 4, comma negative 1. And most of the time, yes, this calculator will take an integral if I don't put in, looks like I'm missing a comma there. If you don't put in the numbers, it will try and take an integral if it can. This one, it wouldn't be able to. But on the AP Calculus exam, anytime you're putting an integral in the calculator, it should be numeric. And we'll evaluate. All right. Let's see here. It's working pretty hard because I forgot to hit approximate, so it's probably going to... Well, there it goes. It'll eventually resolve down the decimals. 1.367. We want to do 3 decimals at least. 1.367. And that's it. All right, let's take a look at another example. A computer is downloading a large file. After 25 seconds, 14 megabytes have been downloaded. Due to network traffic, the file downloading is slowing over time. The rate of the download in megabytes per second is 9 minus the natural log of 2x. How much of the file has been downloaded after 40 seconds? Well, let's let f be our amount of downloaded, okay? F of t is the amount of download. Well, then f prime of t is the rate, right? So we're simply going to say that f of 40, and you know, I'm being a little symbolic here. You could have easily just written an expression and not made up a function name and all that stuff. But that's going to be equal to the starting amount, which was 14 megabytes, plus the integral of when did we have 14? At 25 seconds, to 40 of all the rates. Well, the rate is determined by 9 minus the natural log of 2x. I guess I was saying t. T would have made more sense, I think. But we'll say x for seconds since the download has started. This would not be impossible to do by hand, but let's just use our calculator. So we'll say 14 plus the natural log of 9. Oops, no, it's not the natural log. What am I doing? The integral of 9 minus the natural log of 2x dx from 25 to 40. Diamond, enter. Gives me an answer of 85.520. Okay. All right, let's take a look at this problem. The graph of f prime consists of the 2 line segments in a semicircle shown. Given that f of negative 2 equals 5, find the following. This is kind of classic AP question kind of stuff. They give you this kind of like, well, obviously statement here, like we can see. They just want to cover their bases, I think. Also, it's not really drawn very well. They want to cover their bases and make sure that it's clear, okay, that we're, this is a good indication. Okay, they're telling me what they are, even though they look like it, that I must be using a geometric formula. So just be aware of that kind of thing. F of 0, well, that's piece of cake. We just know that we have to do that f of 0 is equal to, what do we have information of? F of negative 2 plus the integral from there to there. So f of negative 2 is 5. Now let's find the integral from negative 2 to 0. You can see it is a triangle with a height of 1, 2, 3, 4. Base of 2. So 1/2 2 times 2 times 4 is 4, which gives me 9. So f of 2, I could start at negative 2, but why don't we just start at f of 0? F of 0 is 9 plus the integral from 0 to 2 of f prime of x dx. Well, the integral from 0 to 2, I want to say that's the same, right? That's another 4, so that's equal to 9 plus 4 is 13. Then f of 6, let's see here, f of 6 would be equal to f of 2, which is 13, plus the integral from 2 to 6 of f prime of x dx. Well, that is a area underneath the x-axis, so that will be a negative value. And it's a semicircle with a radius of 2. So it'll be 13 minus pi r squared. So pi 2 squared. There's the radius is 2, right, from here to here. But it's a half. So half of that is a semicircle. So that'll just be 13 minus 2 pi. All right, got a practice problem for you to do. Please pause the video and give it a try. Notice they're telling us the areas of each of these little regions here. They're not telling you whether they are positive or negative, though. Okay, so we have f of 0 that we need to figure out. F of 0, we've been given f of 3, so I'll just have to say f of 3 plus the integral from 3 to 0 of f prime of x dx. Now, the integral from 3 to 0 is moving in a backwards direction. A backwards direction. You know, if you think about it, f of 0 has got to be less than f of 3 because look at all these positive accumulations we would have had. So it doesn't surprise me that I have to subtract. So 5 minus 4 is 1. Because if you started here at 1 and added 4, you would get to 5 at f of 3. F of 7, well, that's going to be f of 3 plus the integral. Oops, I wrote a curly brace for some reason. Plus the integral from 3 to 7 of f prime of x dx. Well, that's going to be 5. The integral from 3 to 7 is a negative 9, giving me a negative 4. All right, then f of 9 is going to be equal to f of 7, which is negative 4. Plus the integral from 7 to 9 of f prime of x dx. So negative 4 plus 2, because it's above the x-axis. So negative 4 plus 2 is a negative 2. And next we're supposed to draw a sketch of f. Okay, this will be fun. Let me kind of grab this right quick. See if I can't make it to where I can see a little bit more of this at one time. All right. So, a couple of things. Notice that this is f prime, right? This is f prime. We can start using some of the stuff that we learned when we studied derivatives. That 3 is a relative maximum because f prime changes from positive to negative. So at x equals 3, we were at 5. I think it told us that, right? Let's see here. We go from 5 down to negative 2. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So 3, 5. That's a relative maximum. And at f of 0 is 1. F of 9 is a negative 2. Notice that f of 7 is a relative min, because the graph of f prime goes from negative to positive there. We can even talk about concavity. From up to about x equals 1.5, we're concave up because the derivative is increasing. So concave up, then we're going to switch to concave down. We're going to continue to be concave down all the way until x equals 5, in which case we're going to switch to concave up and hit this minimum, and we're going to be concave up until 8, in which case we're going to switch, and then we'll be level off right there at the end. A pizza with a temperature of 95 degrees Celsius is put into a 25 degrees Celsius room when t equals 0. The pizza's temperature is decreasing. I underline that for us. Don't expect that to be underlined on a test question on the AP exam. Got to read carefully. The pizza's temperature is decreasing at that rate. That's the rate of decrease. Estimate the pizza's temperature when t equals 5 minutes. How do we do it? We start with the temperature at t equals 0. That's 95 degrees. That's the pizza's temperature. Then we're going to take away, because it's cooling, it's decreasing, and we're going to do it from t equals 0 to t equals 5 based on the rate of cooling. Now, this would be something we could actually integrate by hand if we really cared to, but with the e and the decimals and all, this is probably most likely a calculator problem. Let's go ahead and do it. So this would be, let's see here, 95 minus, we're going to be doing the integral here, the integral from 0 to 5 of 6e to the negative 0.1t comma, t, comma, 0, comma, 5. Diamond, enter. 71.392. Remember, always round to at least 3 decimals. You can go more, but don't go less. And if you have more steps to do in the problem, it's better to go more until then. And that's degrees Celsius. All right. All right, do we have any more today? I don't think we have any more in that lesson. So I will see you in the next one.